Hi there folks, and welcome to the final video lecture for the Geodynamics course on the topic of climatic, geomorphic, and geodynamic processes. We're going to wrap things up talking about the tectonic response to erosion. And our goal for the lecture is to just look at some examples of tectonic models and how they respond to different erosion scenarios. We'll start by looking at a case in which there is no erosion. Now this is a tectonic model that might look already a bit familiar in terms of its general setup. We have mass being fluxed in. This is a continent that's essentially coming in from the left side at a velocity of 2 centimeters per year, and over here on the right side we have a continent that's fixed. The two collide, and as a result you form an uplifted region with faults bounding either side of this mountain system. Now, if we look at this model, again, I'll remind you there is no erosion. So here we have had 1.5 times the thickness of the crust in terms of the total amount of convergence, and we've built up a relatively broad area of uplifted topography here in the middle. And this topography is bounded by two shear zones. So the plot we're looking at here in B is a plot of the velocity vectors and strain rates in this model. And so the strain rates, I'll remind you, the bright colors are going to indicate high strain rates. These are essentially shear zones in the crust, or fault zones. You could think about them as being similar to a fault zone in the crust. And so we have our two faults bounding this uplifted plug of material in the middle. If we look here beneath that, there's an example of the temperature field that's shown in the colors there. So you can see cool colors, the blue near the surface, and relatively warmer yellows and orange toward the base, along with this mesh that indicates how the model has been deformed internally. Again, because there's no erosion, we wouldn't expect that mesh to extend up above the surface of the model. And here then in the bottom is the total strain history. And so what you can see is on this shear zone that's on the incoming side in terms of where the mass is coming from, we have an area that's been broadly deformed in a thrust belt type setting, whereas on the other side of the origin we have just a more localized crustal scale shear zone. So that's the picture of the crust and how it deforms in a case when there's no erosion. The opposite end member, of course, to that is a case where we have complete erosion. So any uplift that occurs is immediately eroded. Here, if we look at the sort of velocity and strain rate picture, things look broadly similar in the sense that we have mass being fluxed in on the left side and a pair of shear zones, but it's a much more symmetric system in this case with basically a little V-shaped shear zone, and all of these velocity vectors between the two shear zones have a constant magnitude and orientation. The temperatures, as you might expect, are significantly warmer in this case because we're eroding material at the surface, and so we've basically have very warm temperatures up close to the surface in the region where we have the rapid rates of uplift, and that's a result of advective heat transfer from the upward motion of the crust. And down here, if we look at the total strain history, things kind of look similar in the sense that we've got distributed shear again on the pro side, or the incoming side of the continent, and then more focused shear zone on the side of the continent where it's fixed. So that's our two contrasting models in terms of no erosion and total erosion. Now we'll look at some additional scenarios. And in this case, what we're looking at is something that's actually a bit more like what we saw in the first video lecture on this topic. And this has to do with how the change in prevailing wind direction and precipitation affects erosion in these kind of models. So again, we have mass being fluxed in from the left side, a fixed continent on the right, and they're colliding. The colors are showing you the strain rates. But in this case, we have now a surface process model. Instead of total erosion or no erosion, we have a surface process model where there's now a wet side and a dry side of the mountain system. And the wet side, of course, there would be much more erosion than there would be on the dry side, where there's effectively no erosion. What we can observe here is that we have a large magnitude of material being eroded up. This mesh has been pulled up above the surface, and that's originally where we would have had mass that's been uplifted and eroded away. This essentially shows that when the prevailing wind direction is coming from the right side, we have a large region of eroded material on the right, and just the opposite, of course, when the prevailing wind comes from the left, we have an area of large magnitude of erosion on the left side of the origin. We can also see a few other things here. For instance, when the wind direction comes in from the right, the drainage divide here, the highest elevation point, moves to be the left of this S point, when the S point is basically where this velocity along the base of the model goes to 0. And so this is where our mantle is subducted. And we can see that here the drainage divide's on the left, and when the wind direction comes from the other side, the drainage divide is on the right of that S point. So there's a few other things that are different here. One thing I'd like to ask you at this point is to pause the video and just think about this for a second. If you look at this kind of picture and you think about it as a geologist, what kind of information might we be able to see here? For instance, what kind of rocks might be exhumed in these different scenarios, and where would those rocks be exposed with respect to the structure of this mountain system? So pause the video for a moment, think about that, and come back maybe when you have an idea. Okay, maybe this is a bit of a tricky question. I don't know whether you'll kind of get the concept, but essentially, if we look at this and where we have the largest magnitude of erosion, in the case here where the prevailing wind direction comes from the side of the model where the continent is fixed, we see down here right near the thrust fault that bounds this side of the mountain system is where we have the highest amount of erosion. And that's where we might expect to see very high-grade metamorphic rocks exposed at the surface right near the fault. In the opposite scenario, where the wind direction comes from the other side, we see the largest magnitude of erosion up at high elevations. So it's actually on the equivalent of the same fault, but it's on the wet side of the origin. So we'd expect here to see high-grade metamorphic rocks exposed at high elevations rather than low elevations in the case above. So we can see with this kind of model, not only do we have a prediction about the behavior of a system like this, but we can also make some geological predictions that might allow us to go out in the field and test some of the ideas about whether these models are good representations of nature. So essentially what we're left with is a working hypothesis. And our hypothesis is that climate can affect tectonics through erosion. So by focusing where rain falls on the Earth's surface, we can enhance the rates of erosion, and enhancing erosion at the Earth's surface can in turn change the positions of faults that form in the crust. Now, there are a few questions here that are things that perhaps you can consider now, or you could even consider down the road. And these are ideas like, where can we possibly go to test some of these theoretical ideas? Where can we go to test this hypothesis? What kind of data could we collect? And looking at this then, what are some of the biggest challenges? And I'll tell you right now that there aren't answers to all of these questions. There are some ideas about ways that we can test these hypotheses, but this is very much something that's still a hot area of research activity now. And there are some big challenges, like things that we might observe about the modern day climate may not apply to the million-year timescales that it takes typically for rocks to be eroded during the formation of a mountain system. So there are some big outstanding challenges. What it means for all of us is that there's a lot we don't know about these different processes and how they interact with one another. And there's lots of opportunities to go forward in the future and learn more about these types of interactions in mountainous settings. So that's it for our final video lecture. Once again, as always, it's time to go and take your quiz, and we'll see you for class.